Hello everyone. Welcome to use WaveFormRevealer. This is a tutorial for the function of WaveFormRevealer. After you download it from LAM's website, you will see the following files. The MCR installer should be installed on your computer first to enable WaveFormRevealer to run on your personal computer. After double-click of WaveFormRevealer, this front panel will show up. This is the main interface of WaveFormRevealer. On your up left-hand side, you can see the material library. By clicking that, you can choose the material. Now you can see a bunch of materials showing up here. It also contains the default settings or default values. Let's choose the first aluminum, for example. Now you'll see the material properties, default values, and settings shown up. You can change all these default settings by modifying the material txt file. Let's press Apply Data. By pressing this Apply Data button, you will apply all these material properties and the geometry data to the calculation, and the WaveFormRevealer will calculate the waveform of this engineering condition. We can see the first is sensing signal from receiver PWAS 1. It is 0 at location, means it coincides with the actuator, so it basically shows the incident coming direct wave. And PWAS 2 location is 500 millimeters away from the actuator, so we can see the S0 and A0 package. On the right hand side, we can see the wave speed dispersion curve, and we can also choose the tuning curve, the frequency components of S0 and A0, or the plate transfer function of receiver PWAS 1. This is the excitation signal. It shows here is a 3-count hanging window modulated sine tone burst. The WaveFormRevealer allows you to obtain the waveform of an arbitrary engineering condition. By arbitrary, we mean various material properties, arbitrary plate thickness, PWAS size, actuator PWAS size, and receiver PWAS location. For example, let's change this one to 100. So on the first picture, you will see the receiver signal at 100 millimeter from the actuator. We'll apply data, and then the signal will come out. You can see this is a receiver signal at 100 millimeter from the actuator. Also, we can change the PWAS, the plate thickness, to 1 millimeter and apply data. Then we can see the wave propagation, the wave signal at PWAS 1, PWAS 2, propagating in 1 millimeter thick plate. You see this, we cannot really see the signal, so I can change to 400, for example, to show this time range. And also we can change to 5-count tone burst signal. You see, it's 5-count tone burst. You can also check tuning the frequency components, and the plate transfer function. Now, we can also change the excitation. For example, let's go to 200 kilohertz and to see what the waveform looks like. It looks like this. The waveform revealer has a dynamic response to your input, and it works like an oscilloscope, enabling you to see the response of your pitch catch system to your frequency. That means it will show the different response of structure under different frequency. For example, let's go to a lower frequency, 50 kilohertz, and 3 count. Okay, we should increase the range to see the signal. Now this shows the signal of 50 kilohertz excitation. By pressing this button, you can change the frequency by 1 kilohertz each click. 51, 52, 53. And you can see the signal is dynamically updating according to the frequency. It is like an oscilloscope. You see it's now 66 kilohertz. You can see the excitation signal is changing also. The frequency is changing. This response signal are changing. The receiver sensing signal are updating according to your frequency input. And also, this side, the tuning curve, is also updating. And this line tells you the frequency excitation, tells you where you are, whether you are approaching tuning or not. And also the frequency components is also updating with your input. So this waveform revealer allows you to see the response of your structure of wave propagation under different frequency in a changing and a dynamic manner. The waveform revealer also allows the user to use his arbitrary excitation signal. We have shown the excitation control of the count number and the frequency. We can also select the excitation type. For example, we are exciting in the plate both S0 and A0 mode of wave. We can also excite only A0 mode. For example, now we will only see the A0 mode excitation. So there will be no S0. The S0 packet will disappear. Or we can select to excite only S0 mode. Then the S0 will appear and A0 will disappear. Okay, let's go to the total wave, exciting both S0 and A0 mode. Now we will use two examples to demonstrate this block. This is the input signal. Basically, this allows the users to design his own input signal. For example, let's have a look at a signal of 150 kHz 3-count tone burst traveling in a 1 millimeter thick plate for 100 millimeters. Now we will see the signal here. It looks like this. We can export this signal and save it in a file. So we have a sensor at position 2, but we don't have a sensor at 200 millimeters, for example. Then we want to know the response of the signal of the plate at 200 millimeters. What we can do is we can import this signal, and this division time will basically choose the A0 range. For example, it's 46 to 90. Then we're doing a plate input because we know the sensing signal at the plate point, and we want to know the other point. We're not exciting the plate with PWAS, but just within the plate. Then it shows the signal. This is a signal basically of wave traveling another 100 millimeters away. So that is like this. Also, we can do another thing is like this. We just do a plate input, we can do a PWAS input. We are applying the voltage on the PWAS. This is 180 kilohertz signal traveling in a 1 millimeter plate. For example, let's do this 180 traveling in a 1 millimeter plate. It looks like this. And then we obtain the signal and do a time reverse the signal. This signal is time reversed, and then as the PWAS input, we should choose all the range of the signal. Then we do a PWAS input. What we see here is a reconstructed signal from the time reversal method. The data obtained by WaveFormRevealer is available for you. For example, if you want to obtain the waveform, you just press Save, and under your folder, the 100 kilohertz Excel file will appear, and you see the Excel file. The first column is time, second is the signal of the receiver PWAS 1, third column is receiver PWAS 2 signal. And also this data is also available for you. For example, the save button will save the data of the current showing figure. Let's press save here. Then under this folder, dispersion curve will appear. And for example, if you want to save the tuning curve, still calculating. Saving the file. Okay. For example, if we want to save the tuning curve, we just go to the tuning and press save. And you see the tuning curve appears. All the data are stored in these files. The waveform revealer can also obtain the waveform of lamp waves interaction with damage. This damage information button, by clicking it, you can go to the damage information platform for defining linear and nonlinear parameters of the damage. You can also define the damage location, whether or not include the direct wave. Let's load default data. The default data is with the damage at a location of 200 millimeters away from the actuator. The SST means the S0 mode transmitted from incoming S0 mode, and SAT means A0 mode wave transmitted from incoming S0 mode. This involves a mode conversion phenomena. A0 mode transmitted from A0 mode, and S0 mode transmitted from incoming A0 mode. Also, this is mode conversion. You can also play with the phase. Those are the second harmonic coefficients, third harmonic coefficients. For example, let's do a linear damage. We apply the data here. We can see in the DOS window, we see damage information obtained. Then we apply data here. Then the waveforms will take the damage information. For this PWAS location, the waves will travel to the damage and reflect back, so there will be reflected waves. For this receiver PWAS position, there are the transmitted waves and mode conversion here. We can also simulate the nonlinear interaction with damage. For example, let's give some arbitrary numbers here. Apply data and apply data here. We will see the waveforms will take the nonlinear form. You see the waveform is distorted and there are a lot of zigzags inside. If you do the Fourier transform, you can see the nonlinear higher harmonics. Lamp waves interaction with different kinds of damage will have different phase information. For example, we can change the phase information here in degrees. For example, let's change this to 180 and apply data. We can see the phase change here in the mode conversion. Phase changed. For example, here let's go to 180. Apply data. Phase change will appear. Since we can obtain the waveform in time domain at any sensing location, so we can obtain the spatial time domain wave field. This will allow waveform revealer to work as a virtual laser vibrometer. By clicking the spatial wave solver, we open the guided wave spatial propagation solver. Applying default setting, these values are calculated from the front panel. If you have different settings here, you will get the different default settings here, which guarantees the calculation accuracy. For example, the time range is 0 to 400. We can see the time range is 0 to 300 is enough. So we can put this to 320 to save calculation time. And the spatial resolution, you can define it, maybe 200 is enough, and time step is a microsecond. You can change this time step, and after you click solve, this time-space domain wave field will show up. We can see at 200 millimeters, the wave is transmitted, reflected, and mode converted. And A0 mode is transmitted, reflected, and mode converted. Since we have obtained the time-space domain wave field, we can do the frequency wave number analysis. By clicking here, this will give the frequency wave number domain field. We can see the excitation is at 100. And we can see here, by clicking here, this is the transmitted A0 mode, transmitted S0 mode, reflected S0 mode, reflected A0 mode. We see 100, 200, and 300 frequencies. This 100 corresponds to the excitation frequency. 200 and 300 components are the nonlinear parameters, or the nonlinear damage information. We can see here in this figure, it shows the guided wave spatial propagation. This is the damage point at 200, as we define here. By clicking this button, we can see the wave propagating in. S0 and A0 separate, and interact with damage, with transmission, reflection. We can change this time step by changing this. For example, if we use the 0.5 for the calculation, we click here, it will increase 0.5 microsecond per click. Another thing we can do is we can do an animation. By clicking animation, you will see the wave interaction with the damage. This is spatial domain, reflected wave, transmitted wave, interaction with higher harmonics here. The solution from the guided waves spatial propagation solver is also available for you. For example, if you want to save the time-space domain wave field data, you can just select the figure and click here. This save button works the same way as the front panel ones. You can select the figure you want to restore or the data you want to store, and then click Save Data button. And you can see here in the data file, there is a time-space wave field data up here, and it is updating. Or we can save this data. Click here, go to the folder, you can see the wave frequency wave number field plot theoretical curve appears. Also, we can save the animation. For example, by clicking Save, you will see the wave propagation pattern again, transmission, mode conversion, reflection, mode conversion. And the animation will be saved in the folder. We can see here a spatial wave propagation AVI file appears. The data is saved, and we can play it. Now we obtain the spatial wave field propagation. The waveform revealer is also capable of modeling multimode lamp waves propagation. For example, let's go to a thick plate, 6 mm, and high frequency, 300 kHz combination, and let it propagate for 300 mm. And we press Apply Data. By doing so, we will get the receiver signal with multimode lamp waves. We see here is S0 mode, A0, and A1, because at 300 kHz we have 3 modes, S0, A0, and A1. And we can see the wave spatial propagation. Maybe 200 is enough. We put 200. And we click Solve. Okay. After you obtain the time-space domain signal, you can check the frequency wave number domain. We can see 3 main modes. They are the transmitted A0, transmitted S0, and transmitted A1. So that is nearly all the current functions of our waveform revealer. Thank you very much for watching, and enjoy.